Hello and welcome back to Yeyu Lab. Remember that real-time multimodal project we built? The one where we removed the cloud API from Gemini's Multimodal Live API and create our own local real-time assistant using Whisper, Q1 2.5 and Kokoro. Well, it's time for a major upgrade. We are going to make it feel much closer to the responsiveness of something like Gemini, or even better, this is about achieving a truly natural and intuitive interaction speed, enabling interruptions, reducing the GPU demands. Let's recap. In the previous tutorial, we built a system that could process real-time audio and images, creating spoken responses. The key was using a 3-stage pipeline. The Whisper Small model for the incoming audio, the Q1 2.5 VL7B instructor model for multimodal processing on combine the transcribed text with an image to generate a text response, and a text-to-speech called Kokoro, which is to convert the text response back into the audio and send back to the user front end. This was a big win for several reasons. There's no API limits, no rate limits, no token counting, no session timeouts. Number 2 key reason is the customization, which we could swipe out these models and tweak parameters and add support for new language total control. And also the privacy that all data stayed on our own machine, crucial for sensitive applications. And cost effectiveness, apart from the initial hardware investment or from the cloud GPU rental, there were no ongoing usage fees. It wasn't about replacing the cloud API, and they have their own strengths for sure. This was about providing an alternative, a powerful option for those who need more control, flexibility, and privacy. We used a WebSocket API designed to be compatible with the Gemini Multimodal Live API, so existing projects could be easily reused, especially for the front-end side. Now let's go back to see the previous demo to understand where we are. So I'm going to start screen sharing and pick the blog post of Gemma 3. Hey, what do you see on this screen?
This image shows performance metrics for different AI models across various benchmarks like MMLU Pro, Live Code Bench, and others. It also mentions Gemma 3 with day 0 support in transformers, indicating its ease of integration into transformer-based applications without needing additional setup steps.
Can you describe the column which are the performance benchmarks?
The columns in this table represent different models: Gemini 1, 5 Flash and Pro, Gemini 2.
Oh, I just want to know the MMU Pro benchmark.
9B and 27B, as well as Gemma 3 versions from 1B up to 27B. Each row corresponds to various benchmark tests. Like
Can you tell me only benchmark of Gemini 1.5?
Each model version across these tasks.
Looks the model cannot immediately reflect to the interruption. Yeah, you can feel that isn't quite well as fluid and responsive as, say, Google's Gemini. So here were the key areas that we want to address. First is the response speed. You can feel very obviously that there was a noticeable delay between the speaking and hearing the AI's response. So it's not so immediate feedback for the real-time interaction. The second is the interruptibility. If you start speaking while the AI is also talking, it wouldn't stop it. You had to wait for it to finish the entire response, which isn't how natural conversations work. And third, you cannot feel from this demo, but it's really happening, that the GPU requirements is not a little thing. This version will need a GPU with at least 17 GB of VRAM, which could be a barrier for some users. So when we look at this system diagram, it's clearly that from the beginning, the audio and image data flow from the client browser to the server via a WebSocket connection as usual, and the audio segment detector module identifies the segments and triggers the whisper transcriber segment to do the transcription, and then the transcribed text along with the image data feed into the Gemma 3 generation block for the multimodal recognition. And here we will see the parallel processing that and I have introduced before for the streaming handling to accelerate the response speed. And here is a cancel tasks that's triggered by the new speech during the processing of the old speech that is using to handle the interruption scenario. Then all the text output goes to Kokoro TTS module to make a human-like speech and send this initial audio back to the WebSocket connection to the client. In this project, we have addressed all these three challenges to make our voice assistant really like the natural conversation. So towards the first challenge, which is the slow response speed, it's mainly because of the waiting for the entire response to be generated and then synthesized by the model. So our solution is to use the streaming and parallel TTS to let the model generate text token by token, and we immediately begin synthesizing speech from the initial portion of the response text, and then do this in parallel with the ongoing text generation. This means the user starts hearing a response almost instantly. The remain text is then synthesized blocks by blocks for higher quality output once it's available. The second challenge, which is the lack of the interruptibility, our solution is to deploy an interrupt handling mechanism to continuously monitor the new speech input even during the TTS stage. If new speech is detected, our cancel tasks is called. This immediately cancels any ongoing multimodal generation or TTS processor and give a signal to the front end to stop any ongoing audio playback. And then the system can process the new speech input and respond to new speech output to the front end, which is the solution for the interrupt handling. And for the high GPU usage, we replaced the original Q1 2.5 VL 7B to Gemma 3 4B model with 8-bit quantization to dramatically reduce the usage of the VRAM from 17 GB usage to 8 GB almost. Now let's try the new demo to see the improvement, especially for the response speed and the interrupt handling. Let me share the screen with the model. So let's start share a screen, which is the Gemma 3 blog post again. Hi, how are you?
I'm doing well, thanks for asking. It's nice to chat with you. Is there anything you'd like to know about this image?
Can you describe this image?
Okay, let's take a look. This image is a comparison chart of different Gemini models alongside Gemini 1. 5 models It shows performance metrics like MMMLU, live code bench, and others. Do you want me to highlight any specific model or metric?
Yeah, can you describe the Gemma 3 performance?
Okay, let's take a look at the GMS3 performance. It scores a solid 48.
What about
8 on
its
MMU
mass
val,
performance?
with 47. Okay, let's take a look at the mass performance data.
Okay, so it looks the response speed at the first sentence is very good, and also when I interacted with a new topic, it can reflect this interrupt very properly. And for the better use, I recommend to use a headset to make sure the echo and unnecessary interruption into the conversation loop. And you can also see that the usage of the GPU is only 8 GB VRAM. That's a very small usage of the computing resource when we use even 3 models, including Whisper, the large, Gemma 3, and the Kokoro. Now let's check in the code. We will focus on the most important parts that we have improved from our last project, but most key functions will be covered, especially for this server-side implementation. About the front end, you can download from my GitHub repository for the latest front-end demo in React framework and use it for free. And for the server code, you can also download from my GitHub repository to test. So first, let's see the audio segment detector, which is the first stage of our workflow. The new changes inside this stage is what we set and cancel current tasks to make sure the interrupt handling implementation. So for the cancel current task, this is a very important function which cancels any ongoing generation and TTS tasks. For the set current tasks, which keeps track the currently running generation and TTS task. Generation means the Gemma 3 generation. Okay. And in the add audio function, which is now also checking the TTS playing signal before adding the speech segment to the queue, if the TTS is active or a generation task is running, it calls the cancel current task to immediately interrupt the AI generation. This is the core of our interrupt feature. There's nothing changed in the Whisper transcriber because it's the first stage to detect and convert the voice data to the text data. Let's see the Gemma Multimodal processor, which is a replacement of our previous Q1 2.5 VL model to do the job of the multimodal generation. Inside this generation, compared to the Q1 2.5 version, we have implemented a generate streaming function instead of original generate function to make sure the streaming implementation has been done. It uses the text iterator streamer function from the transformers library to receive text token by token. This generation process is started in a separate thread to avoid blocking the main event loop. It collects the initial text until it's finding a sentence end using a regular expression or reach a maximum character count defined by min chars. This ensures that we have a coherent chunk of the text for the initial TTS processing. It returns the both streamer for continued generation and initial text for audio playback. And here I add the build messages and update history function to manage the conversation history, allowing the Gemma 3 to remember the previous turns in the conversation, which is a very important concept in the Gemini as session implemented in our local deployed version. Now let's move to the Kokoro TTS processing, which is doing the text-to-speech conversion job. So the most important change is that we defined synthesized initial speech and synthesized remaining speech that play with our streaming mechanism to make sure the TTS conversion can be start as early as possible when the initial text arrived. And the remain text arrived, it should keep going with the remaining conversion. And now let's move to the handle client, which gathering all the subtasks in together and orchestrating them in a real-time and reliable sequence. So here we have a new message type defined to signal the front end when we have an interrupt arrived. In the JSON format, it only have one key interrupt and the value true. If you design your own front end, you should be taking care of this message to ask your front end client to stop the ongoing audio when the interrupt message comes. And the rest of the message, like audio message and image message handling, are pretty much the same. So here I also add some mechanism to skip and filter out unwanted transcriptions like the punctuation, single words, and some sounds that passing from your microphone, which will impact the quality of the audio responses. Okay, that's it for the code. Again, the updated code and the previous code are all available from my GitHub repository that's listed in the description below. You can check in the source code, download the demo, run the demo, or build your own project based on that. Welcome for the comments, and I will see you in the next video.